Now we'll talk about net ionic equations. So the purpose of a net ionic equation is to show exactly what's going on in a reaction, exactly what's changing in a reaction. The ions that are combining to form, it's either going to be your precipitate, the solid, the liquid water, or one of those insoluble gases I just talked about. You'll end up crossing out spectator ions, so they're not going to be shown. And then this is key. If your compound is aqueous and ionic, it splits apart into ions. If it's a solid, liquid, or gas, it stays together. We can make one little note here. If it's aqueous and ionic or aqueous and an acid, it's going to split apart into ions. Okay, but if it's your precipitate, if it's your liquid water, or if it's your insoluble gas, it stays together and does not split up. That's important. When I do this example, I'll actually first be writing a complete ionic equation. So I'm just going to split apart all of my aqueous things and keep together my, in this case, solid. So Pb2 plus, all of these ions are going to be floating around in water, so they'll all be aqueous. NO3 minus, that's the nitrate ion. There are two of them. That subscript becomes now a coefficient to show that there are two separate NO3 ions floating around, or moles, I should say, of them. Now this coefficient gets distributed, so 2 K plus ions and 2 I minus ions. Okay, your PbI2 stays together. It's not going to split apart. Solid, that's your precipitate. And then your last compound is aqueous, so 2K plus and 2NO3 minus, and those are both AQ. Now, what we have here is a complete ionic equation. In order to get from complete to a net ionic equation, you're just going to cross out your spectator ions so that they're no longer shown. How do you know if it's a spectator ion? If you have exactly the same thing on the reactant side as you have on the product side. So here we have Pb2 plus, but we don't have exactly that on the product side. Okay, we have the lead ion that's hooked up in a precipitate, so we cannot cross out Pb2 plus. What we can cross out is the two nitrates. We can also cross out the two potassium ions, and then we can't cross out the two iodides. So we are left with lead 2 ion plus 2 iodide ions yields PbI2, which is your precipitate. So the final answer is your net ionic equation. Okay, do you have to do the one in pink, the complete ionic? No, but I think that's a good way to learn what a net ionic is. The product of your net ionic equation is always going to be your solid, your liquid, or your gas. We'll now do an example with the formation of an insoluble gas, the carbon dioxide. So remember, this product together would have been carbonic acid, H2CO3, but that immediately splits apart into carbon dioxide gas and liquid water. I'll start writing the complete ionic equation. So barium carbonate will not split apart because it's starting out as a solid, so it'll stay together. However, your nitric acid will split apart into the ions. So 2H plus, those are going to be AQ, and distribute the coefficient, so 2 nitrate ions. And then on our product side, you'll have the barium nitrate splitting apart. And then you'll get 2 nitrate ions. And then neither your CO2 nor your liquid water will split apart. They'll stay together. Okay, so when we come in to get our spectator ions out of there, the only thing that's exactly the same on both sides is your 2 nitrate ions. So everything else that I'm underlining in blue stays there for your net ionic equation. So here's an example where there's like a lot of stuff that's still present in your net ionic equation. And again, the net ionic equation is kind of it's only looking at the components in your reaction that actually change.